Novel view synthesis with sparse inputs poses a challenge for 3D vision. Although recent advances in NeRF have excelled in reconstructing scenes from just a handful of input views, previous works are mostly slow and costly. Nowadays, 3D Gaussian splatting exhibits its potential for sparse view reconstruction with high efficiency. Nevertheless, the reduced input views would significantly degrade geometry and cause failure. Inspired by the success of earlier depth-regularized sparse-view NeRFs, this paper explores distilling depth information from pre-trained monocular depth estimators to rectify the Gaussian fields of the ill-learned geometry. Our framework starts from a random initialization and consists of a color supervision module and a depth regularization module. The optimization process of color supervision mainly inherits from 3D Gaussian splatting except for a neural color renderer. In the depth regularization, we render a hard depth and a soft depth for the input view, and separately calculate the losses of the pre-generated monocular depth map with the proposed global local depth normalization. Finally, the output Gaussian field enables efficient and high-quality novel view synthesis. Despite sharing a similar form of depth rendering, the depth regularization for 3D Gaussian radiance fields differs significantly from that employed by NeRF. Firstly, simply using the depth map to regularize all parameters, which is widely used for NeRFs, would cause oversmooth and blurry details in 3D Gaussian radiance fields, since this practice would force the shape of Gaussians to fit the smooth monocular depth rather than the complex color appearance. To solve this problem, we first suggest freezing the shape parameters, which helps preserve fine appearance details. Then, we propose the hard and soft depth regularization that achieves a balance between accurate geometry and delicate appearance. Compared to NeRFs, eliminating small depth errors is important but more challenging in 3D Gaussian radiance fields. Our proposed global local depth normalization refocuses on local depth differences, and thus helping build a clean surface. Our DNGaussian can efficiently fit a single scene from the LLFF dataset in just 3 to 4 minutes. This is a significantly shorter time compared to the current SOTA methods, which often take more than 1 hour for the same task. Attributed to the high-efficiency scene representation, DNGaussian achieves real-time rendering over 100 FPS on PC with RTX 2060 GPU. This speed can even increase to 300 FPS on a single RTX 3090 Ti. In the following, we will show more visual results. Thanks for watching.